because of its key role in the Schrödinger equation, the Hamiltonian turns out to be very useful for telling us what will happen in the future. We're going to look here at one formal relation and how we do that. This particular relation is not so much for solving problems. Indeed, if we want to figure out what will happen in the future, we already know how to do that. We just integrate Schrödinger's time-dependent equation. And this formal relation does not really help us do that in a practical sense. The usefulness of what we're going to do now is more conceptual, and we will be coming back to this conceptual idea many times as we go forward here.
Taking Schrödinger's time-dependent equation, so here's Schrödinger's time-dependent equation over on the right, and simply rewriting it by moving the IH bar about, and presuming that the Hamiltonian operator does not depend explicitly on time. That really means in Schrödinger's equation that the potential doesn't depend explicitly on time. Could we somehow legally rewrite this form here? Now, let's look a little bit at why we would even think of doing that. If the Hamiltonian operator h here was simply replaced by a constant number, then obviously we could take this equation, pretending for the moment this was just a number, and we could integrate it. And the result of that integral, pretending h was just a number, would just be this expression here. This is a simple differential equation, and pretending this is a number, we'll get this form as the result. And you could check that by differentiating back in here. Now, if with some careful definition we could figure out a way in which it was legal to do this, then we would have figured out an operator that gives us the state at time t1 directly from that at time t0. And to think about this legality, we're first going to note that because h is a linear operator, then for any number a, we can move that around. That is, h operating on a times a function has to be the same thing as a times h operating on the function. That's one of our basic properties of a linear operator. And since this works here for any function, we can do this operation of moving the a around here for any function psi of r and t, then as a shorthand, we could write h then a is the same thing as a then h. We have to presume when we write these kinds of operator equations that the operator equation works because it works for every function that it might operate on, and that's certainly true here. Next, we have to be careful and define what we mean by an operator raised to a power. This in itself doesn't necessarily have any meaning until we're careful to define what we mean by it. So if we mean by this notation that h squared, we mean h operating on the result of h operating on the function psi. So h squared here we take to mean this, provided we define that notation, then we can get somewhere with this. Specifically, for example, for the energy eigenfunction psi n of r, then h squared operating on psi n of r, we're saying what that means is h operating on the result of h operating on psi n of r. That's h operating on en times psi n of r. But because this h operator is linear, we can move that en outside here. So that's en times h operating on psi n of r. H operating on psi n of r is again en times psi n of r. So h squared operating on psi n of r is en squared times psi n of r. And we can proceed in the inductive fashion, to define all the higher powers, that the m plus 1th power of h is h operating on the result of h to the m operating on the function of interest. So it seems kind of obvious, but we have to be rather careful to define what we mean by this notation, and this is what we mean by it. And so, for example, then, h to the power m operating on an energy eigenfunction will give us the energy eigenvalue en to the power m times that same function. So let's look at the time evolution of some wave function psi of r and t between times t0 and t1. Suppose the wave function at time t0 is just in space this one particular function here, psi of r, whatever that is, and we can expand that psi of r in the basis functions, the energy basis functions, eigenfunctions. So we get some set of coefficients, an times psi n of r. Then we know that once we multiply by the right complex exponential factors for the time evolution of each of the basis functions, and those are the complex exponential factors here, then we have what is going to happen in the future. We knew what the wave function was at this time. We expanded it in these energy eigenfunctions. We multiply by the correct complex exponential factors. We add everything up. We're going to know what the wave function is at this later time, t1, from what it was at this earlier time, t0. Now, in this expression here, we can note that perhaps we can write out the exponential as a power series. So the power series for an exponential is what we have here, 1 plus x squared over 2 factorial plus x cubed over 3 factorial. And if we do that, then this expression that we figured out is just a standard expression for the time evolution of this superposition of energy eigenstates. This expression with the exponential we would rewrite in the following form here. So here's our x, this argument, and we keep raising this x to higher powers, x to the 1 here, x to the 2 here, divided by the 2 factorial, and so on. Now, in this expansion we've just written down here with our exponential written out as this power series, because we showed that h to the power m operating on psi n of r was just en to the power m times psi n of r, we can substitute here to obtain this expression. So everywhere we had en times psi n of r up here, we can put h times psi n of r here. And every time we had en squared times psi n of r, we can put h squared times psi n of r. So we're sort of working backwards from the right-hand side to the left-hand side of our Schrödinger-like equations, or working backwards from the right-hand side here to the left-hand side. And of course, with this expression here that we've just written down, because h and all its powers commute with scalar quantities, that is numbers, we can rewrite this. So we can move the an over here, move the whole summation over to the right-hand side here. And hence, psi of r at time t1 is everything we see here operating on psi of r at t0. So, provided we make a notational definition that what we mean by the exponential of the operator is in terms of the power series, that what we mean by this, we're just making up this notation if you like, that what we mean by this thing where the exponential has got an operator in the exponent, we mean this power series, and we've carefully defined what we mean by the powers of an operator, then we can rewrite our preceding expression, the one we just had on the preceding slide, that psi of r and t1 is the exponential of minus ih, the operator, times t minus t0 over h bar, all operating on the wave function. Because we made this notational definition to give this expression some actual meaning, then we can write the following expression down here. Hence, we have established that there is a well-defined operator that, given the quantum mechanical wave function or state at some time t0, will tell us what the state is at some later time t1. And here is the expression that does that. Here is our time evolution operator. So this time evolution operator operates on the wave function now to tell us what it will be in the future. Incidentally, this will also work backwards if you like. If you know the wave function now, this will tell us if t1 is earlier than t0, it will tell us what the wave function was in the past.
So what we have really established here is that in quantum mechanics, there is an operator that we can formally apply that mathematically changes the quantum mechanical state from what it is now to what it will be at some future time. We have deduced a time evolution operator. This operator, like the others we are working with, is also a linear operator. Incidentally, it also preserves the normalization of the wave function. If the state is normalized now, then the one we get in the future by applying this operator is also normalized. We will be returning mathematically to these ideas later. The important point for the moment is just that we have devised a linear time evolution operator in quantum mechanics, and it's based entirely on the Hamiltonian operator. This link between the Hamiltonian or energy operator and what happens in time is a profound one in quantum mechanics.